Started.
All right, good afternoon, everyone. My name is JP Powers. I'm a research data scientist in the TRAX Data Science Lab, and today we are going to talk about when AI fails in health research. I'd like to open with a story. So recently I submitted a funding proposal to NIH, and I imagine this is what it looks like when NIH distributes their funding. So while preparing this proposal, one colleague asked me if we could budget for cloud computing credits, the idea being that we could give users a small allowance to explore the cloud tools that we would be developing. I said I would look into it. But rather than deep diving into the documentation of one cloud provider after another, I decided to start with an LLM. So essentially, I asked this LLM, is there a way? What's that?
Yes. Amazon.
Okay. So in short, I asked this LLM, can we purchase cloud credits that we can then later distribute to independent users? And in short, the LLM answered, yes, here's the method for how to do that. So I go back to my proposal group. I say, good news. It seems like we can do this after all. And they're like, all right, let's take a look at the method. We start trying to implement this. We can't find the options that the LLM has told us about. My suspicion grows. I dig into this a little bit more and find out that what the LLM told me was apparently formerly a sound way to perform this that was no longer supported. So I go back to my LLM, I describe what it told me, and I said, is this a deprecated method? And it says, that's right. There's actually no way to do what you are trying to do anymore. And I said, cool, I'm glad we figured this out before we submitted this proposal with tens of thousands of dollars in the budget towards a process that doesn't exist anymore. So the moral of this story is really the moral of this whole presentation. And for that, I refer you to the 2002 Spider-Man film directed by Sam Raimi. So everything you need to know is in that film. With great power comes great responsibility. AI is very powerful, but knowing when and how to use it is critical. If we had submitted a screwed up budget on the word of an LLM, it would not have been the LLM taking the fall for that mistake. The responsibility would have fallen to me, the user. So successful use of AI requires both technological solutions and human considerations. And this is what we'll be revisiting throughout the talk today. So we're going to cover the tension between the benefits and the risks of integrating automation and AI into our workflows. We'll talk about ways that ML implementation can go wrong, trust issues when dealing with research literature, and some of the human costs of AI in contexts like this. But first, we'll review a few core concepts to make sure we're all on the same page, starting with AI. So this refers to technologies that enable computers to perform tasks that somewhat mimic human-like abilities. So this can include things like generalizing from examples, predicting outcomes, classifying cases into a certain set of categories, using human language, and adapting to changing stimuli. So for that, you can think about cases like autonomous vehicles and other AI-based robotics. So here, AI is the biggest umbrella concept of these related concepts. And then machine learning is a subset of AI techniques. Similarly, deep learning is going to be a subset of techniques within machine learning. And from deep learning comes the generative AI applications that we're familiar with, like large language models. And then machine learning is when we use algorithms to learn from examples how to perform some task. So we have our set of examples, our data set, and there's all sorts of associations that exist in those data between different elements. So we can develop a specific model to pull out the patterns that we're interested in, and then use that model on new data to perform some sort of task. So to make this more concrete, let's say that our example data set consists of electronic health records from patients who have inpatient encounters. And the patterns we're specifically interested are associations between patient level and encounter level features and readmissions. So we develop a model that can learn those associations of interest, and then we can use that model on new data to do something like predict the risk of readmission within 30 days of an inpatient encounter. And then lastly, large language models, as we said, come from deep learning. And these are models that can interpret and generate human language. So these are our ChatGPT, Gemini, Llama, Claude, etc. So there are chatbots that are trained on vast amounts of information from the internet, and we can interact with them via a prompt, and they'll return a response. So with that, let's dive into our first topic, looking at some of the tensions between the benefits and risks of automation. But to give us some context, let's first review some of the main motivations people have for wanting to integrate automation into their AI workflows. So one of those motivations is productivity. So this includes concepts like efficiency of time and effort, as well as savings on cost, and things like capacity, where sometimes automation can just achieve outcomes on a scale that would not be feasible with manual human labor. Another main motivation is objectivity. This includes concepts like consistency, where if you have algorithms that run on an automated set of rules, they have to perform according to those rules in the same way every time, you can be assured of a consistent outcome, unlike what you might get with human variance over time. Similarly with accuracy, if that algorithm achieves an accurate outcome, you'll be then guaranteed to get the accurate outcome every time, avoiding sources of human error. So automation touts some compelling benefits, but can you really trust it? So Stefan Strauss is an Austrian social and computer scientist, and he's published some work on the balance between trust and scrutiny in the context of automation and AI, and the forces that act on this balance. For example, the more we're willing to trust our automation, the more utility we can get out of it, the less effort we're going to spend rechecking its work or performing its work ourselves. But at the same time, the more we weigh towards the trust side of this scale, the more risk we're assuming, as there's greater chance of errors coming into our results that we would not find. So Strauss goes on to describe a couple forms of bias. First, a well-known form of bias called automation bias. This is the tendency that many people have to accept computer-generated outcomes without question. And this may come as a little bit of a surprise to some of you that work with computers a lot, but to the broader population, a lot of people have this notion of computers as essentially a souped-up version of a calculator. And when you put something into a calculator, you expect it just gives you the same result every time. There's no subjective aspect to it. So a lot of people are used to thinking about computers in this way, and therefore trusting their outcomes without question. And then Strauss goes on to develop this a little further with what he calls deep automation bias, which is really this automation bias being applied in the context of AI and machine learning, where because these processes have even more complexity and opacity, that will even further deter users from scrutinizing them, either because those users don't even know where to start with how to scrutinize them, or because it would be so effortful to do so. So biases like these further weigh down the trust side of this scale and push a lot of people towards avoiding scrutiny of the outcomes that they get from automation. So if we really commit to integrating and trusting automation, what might that look like? An anthropologist at Yale, along with a social and cognitive psychologist at Princeton, have explored this question, and they present a very cautionary take on this. So they posit that individuals who trust AI tools to overcome their own cognitive limitations become susceptible to what they call illusions of understanding. So after a while, people start to forget that an automated tool did a lot of the thinking for them, and they feel that they understand the result or the reasoning that led to it more than they actually do. They argue that the integration of AI tools risks introducing a phase of scientific inquiry in which we produce more but understand less. And part of that understanding less are those illusions of understanding. But another part of it they discuss is that AI tools have a tendency to converge on heavily explored scientific topics rather than diverging into novel research directions. So they offer that technological solutions alone cannot eliminate all risks related to AI. AI systems are created by and used by humans. So human thought and expertise are still critical for accuracy and especially for innovation. Now, thinking specifically about AI in the health domain, a group of informaticists and clinicians explored concerns related to machine learning-based clinical decision support systems. And some of the concerns they raised were the de-skilling of clinicians who become dependent on machine learning support. Simply the idea that without practice of these skills that they've developed, those skills can atrophy over time. Also, that machine learning models can only use the data that they're given. The data they're given doesn't cover everything. It could be missing meaningful context, and the data they're given don't always represent ground truth. Sometimes they might represent clinical interpretations that then got entered into the data system. And then finally, there are some machine learning models that are more black box in their nature. And for these, it's more difficult to catch flaws that might be occurring in their processing that then results in outcomes that are inaccurate. So this group used a few different examples to support their arguments, and I'll just highlight one of them here. So they talked about a group of researchers who trained a series of machine learning models to predict mortality risk in pneumonia patients. And as I say, they trained a series of models. Some of those models were more explainable, so it's easier to determine what was driving their predictions, while other ones were more of those black box types. Now, concerningly, they found that pneumonia patients with asthma were being assigned lower mortality risk than those without asthma. And because some of the models that they used were more explainable, they were able to catch this and dive in and understand what was happening, which was that the pneumonia patients in the training data sets from the hospitals where the data came from, those that had asthma tended to be admitted directly to the ICU. So they were receiving more intensive care overall and achieved better outcomes than the pneumonia patients that didn't have asthma. So a group of clinical research industry professionals quickly published a rebuttal to this Kubica et al. Paper. And they tried to reframe the issue here as that machine learning models are not meant to be replacing clinical expertise. They should be integrated with it or be complementing it. And they argued that the Kubica et al. Paper painted machine learning in an overly negative light. So they said that machine learning, there's nothing inherently flawed about it. The issue is in whether or not it's being applied in appropriate ways. And they also pointed out that advances are being made in the explainability of the predictions of machine learning models. And here it's important to keep in mind that both of these papers are actually almost a decade old now. So explainability in machine learning modeling is something that is making a lot of advances, although it's still an ongoing area and something to be keeping track of. All right, so computers are objective, true or false? So we noted before that objectivity is one of the key motivations that guide interest in automation and AI systems. And this is captured in this statement from a group of clinical researchers. A computer algorithm could objectively synthesize and interpret the data in the medical record. So this is being opposed to such data being subjectively synthesized and interpreted by a clinician who will inevitably carry some biases. So this sounds somewhat reasonable, but it's good to step back and remember what an algorithm is exactly. So it's a process or a set of rules that's going to be carried out in a consistent way. But that raises the question, where do these processes or sets of rules actually come from? And in the case of machine learning, of course, they come from the data that we feed the model during training. And we feed those models data that can contain all sorts of biases. And biases in the input data can translate into biases in the model output. For example, people with more barriers to healthcare access are not going to be as well represented in those healthcare data sets. Data patterns can also vary by context, so patterns that hold in one healthcare system may not hold in another. And then the data generation processes that populate all these data can be influenced by things like clinician biases or even just simple data entry errors. So algorithms and models may execute in an objective way, but the results that they produce can be as biased as the data that were used to train them. So one well-known example of this involved a particular healthcare algorithm that was designed to identify patients upon admittance that would need more intensive care management programs. So it was eventually discovered that there were white patients being flagged for this more intensive care, while Black patients that seemed to have the same disease burden were not being flagged as often. And it turns out this was because the model was trained to predict healthcare management need using healthcare expenses as a proxy for that concept. So the Black patients had, with the same comorbidity burden, had patterns in the training data set of lower healthcare utilization and therefore lower healthcare spending. So because of how this model was trained, it was actually perpetuating racial biases in healthcare utilization in its output. So to wrap up this section, we'll turn to a couple computer scientists at Princeton who posit that machine learning modeling is the chainsaw to the hand axe of statistics, powerful and more automated, but dangerous if used incorrectly. So statistical methods, they argue, in general, risk being used erroneously, but this risk is all the more amplified for AI due to its complexity and sometimes black box nature. And this is especially the case when researchers who have limited experience in skills like computer science are trying to use off-the-shelf AI tools. So it's easy for these types of researchers to overestimate the capabilities of their AI tools, ultimately leading to illusions of progress, stalling real progress. So they conclude that machine learning is not a plug-and-play technology for scientists, but is really a set of methods that still requires deep expertise and continual training. So this leads us to our next topic. What are some of the common ways machine learning implementation tends to go wrong in healthcare research? And the first thing we'll talk about is data leakage, which is one of the main issues that arises in applications of machine learning. So in short, this refers to when you let the model cheat in some way during its training process. So you'll recall that when we train models in machine learning, we split our data sets into training data and testing data. The idea is the model is only allowed to view data from the training set during its training process, and it shouldn't see the testing data at all. That way, we can then use the testing data on the trained model to see how it will perform on data that it's never seen before. And we use that as a proxy for how well the model might perform when it's deployed in a real-world setting. So one form of this data leakage is called target leakage. This is when training data contain information that somehow relates to the outcome that they wouldn't really have when they're deployed in a real-world scenario. Another form is train test contamination. And this is where the model sees information from the test data during the training process. And this is not always as straightforward as rows from the test data were somehow copied into the training data as well. It can actually occur in more subtle ways, like you simply performed pre-processing steps on your whole data set before it got split, which means that part of the way the data were prepared in the training data set was dependent on some of the data in the testing set, which is not allowed here. So these can be trickier to spot than they might seem at first. So we will take a look at a couple examples here. And the first one comes from a meta-analysis comparing the performance of brain MRI data versus clinical data for predicting depression treatment outcomes. And when I say clinical data here, that refers to depression scale scores, demographic features, duration of depression episodes, and things like that. So one research group did a critical analysis of this meta-analysis, and they noted that about 40% of the studies included in the meta-analysis had indications of data leakage. In particular, was a common issue where the research teams were choosing the predictors they were going to use in the model based on the relationships that those predictors had to the outcome in the overall data set before it was split. So that ends up being a very common source of this type of data leakage. And this would be an example of the train test contamination. So the group that did this critical analysis reanalyzed the data, excluding those problematic studies, and as expected, the performance of the models was much lower as a result. Another example concerns machine learning models, a machine learning model for predicting hypertension that was published a while back. So in this case, the model's trying to predict incident hypertension within the upcoming year based on electronic health record data. And the model was performing very highly as it was published. And the authors discussed some of the features that went into the model, including the demographic features, chronic illnesses, and mental illnesses. But soon after, another research group decided to take a deep dive into this study and the publication, and they even went into the supplemental content. And they found there a table that ranked the importance of all of the features in the model. And what they saw there was something that was not mentioned in the main paper, which was that 5 out of the top 6 features in the model were antihypertensive medications. So these types of medications are generally prescribed to people who already have hypertension. So these medications were functioning as an excellent predictor of the outcome because they're really a consequence of that outcome. So the temporal sequence here of predictor and outcome is broken. So what the model was really finding was cases where the diagnosis was just missing in the patient's record, but they already had hypertension, rather than truly predicting cases of hypertension that were going to emerge in the near future. So this is an example of target leakage, where the model's seeing information related to the outcome that it shouldn't be able to see in the intended use case in which it would be employed. So a major key to avoiding target leakage is always thinking through the timing of how the predictors relate to your outcome. And this last example is a little less straightforward of a case. You could actually debate whether or not it should be considered a case of data leakage. So here, there was a research group that was noting a lot of machine learning models were being published with high performance for diagnosing Parkinson's disease. But what concerned them was that a lot of these models included diagnostic features of Parkinson's disease among their set of predictors, things like tremor and rigidity. And so these researchers presented a demonstration where they showed that when you remove these features, then the models perform quite poorly, actually classifying most healthy controls as disease cases then. So they really question the utility of models like these, stating that real utility would be a machine learning model that can find subtle patterns in data from before the patients are expressing overt symptoms that clinicians can already diagnose. So machine learning models that are just reconstituting the diagnostic criteria we already have are of very limited use. So this brings us to our next point, which is that statistical significance does not necessarily imply clinical significance. A group of clinical researchers discussed how machine learning techniques compare to traditional statistical techniques in relation to this question. So they point out that machine learning techniques tend to flourish in capturing nonlinear relationships and complex high-dimensional relationships. Whereas some medical prediction problems are inherently linear, and traditional statistical techniques already capture linear relationships quite well, and in some cases can be much easier to interpret. So in cases like these, it's unlikely that machine learning is really going to buy improvements to any degree that they would impact clinical decision making. Another problem in health research applications of AI is what I'll call the small data problem. So we hear about big data in relation to AI, and this is because the true potential of AI methods is realized with big data sets. For example, Facebook's facial recognition software used over 1 billion user photos in its training. Self-driving vehicles are trained on billions of miles of road traffic video. And to take an old school example, the Deep Blue chess computer program was trained on millions of games of chess. So this is in contrast to something like clinical image classification problems, where these models are often trained on thousands or maybe only hundreds of images. To be fair, though, the examples on the top row here are trying to solve much more complex problems than a basic classification, which is what would often be the case for a clinical imaging study. So these clinical research cases wouldn't need data necessarily on the same scale as those examples on the top row. Nevertheless, their potential will still be limited by data sets that are too small. And the last point here comes back to the issue raised by those Parkinson's disease models, where at the beginning of the COVID-19 pandemic, there were hundreds of studies published of machine learning models for COVID prognosis and diagnosis based on routine X-ray and CT imaging data. Now, note that many of these studies were done before the widespread availability of PCR testing. Otherwise, there wouldn't have been as much motivation for these studies. But since this time, a number of research groups have critically reviewed this work, and they found problems with insufficient sample size, overfitting, inappropriate performance evaluation, inappropriate handling of missing data, and in some cases, just not enough detail being reported in the publications to evaluate the methods that were used. So in some cases, the models actually learned spurious associations based on irrelevant features. For example, many of the studies used a particular pediatric imaging data set for their control cases, but then developed models for adult COVID cases. So the models just learned to distinguish adult from pediatric imaging rather than learning to distinguish true differences in disease states. So this led one of these critical reviews to conclude that none of the models identified are of potential clinical use due to methodological flaws and/or underlying biases. And this is a serious issue when you think about all of the time and effort and funding that went into hundreds of studies. And it recalls that point from earlier that proper use of AI techniques like machine learning requires substantial expertise and training and cannot be thought of as plug and play techniques for research at this point. So we've been talking about ways that research can be afflicted with significant problems, and sometimes those problems result in research papers that need to be retracted. So there's a significant body of research around scientific paper retractions, largely facilitated by the Retraction Watch database. And it's well known now that many research paper retractions are due to errors in data processing and analysis. For example, in the field of radiomics, one author notes the integration of high-dimensional radiomic features and machine learning is what makes this field especially prone to unintentional errors that may warrant retraction. More specifically, there's an absence of standardized pipelines, and this complicates model development and can introduce methodological flaws, such as our old friend data leakage, such that potentially 10 to 15% of all radiomics publications may be affected by such issues. So several researchers have noted that while the overall rate of scientific publications has grown, the rate of retractions is growing more quickly. And one group specifically studied retractions within clinical and translational research. So they noted that with the growth of team science and big data, the increased complexity of research may make these preventable errors, such as those involving analytic methods, more likely to occur. For example, here's a statement from one of the retraction notices that they reviewed. Through the automated process of the analysis, the authors mistakenly failed to identify that their values were inverted, and thus the direction of changes in the individual gene analysis is opposite to those reported in the article. So for this study, the authors reviewed 786 articles from 2011 to 2020 that were retracted for reasons related to data processing and analysis. And a couple of the findings they noted were that 38% of the retracted articles did not specify what statistical analysis software they used, and only 1% of those articles reported sharing their code or using some other sort of tool to support reproducibility. Now, nowadays, I think we would expect the number of studies that share their code to be much higher than this. It's important to remember that all of these reviewed studies are from 2011 to 2020, and many journals are pushing authors to share their code at this point. But nevertheless, this led them to recommend rigorous use of reproducibility checklists and thorough code documentation. And these are the sort of best practices that we hear all the time, but they're still often not implemented, which begs the question why. And data science professor Henry Han decided to address this question from a game theory perspective in his article, Challenges of Reproducible AI in Biomedical Data Science. So in his article, he describes this tension between collective scientific interests and individual scientific interests. So collectively, we would like to see rigorous reproducibility standards implemented because this would lead to more verifiable and trustworthy research, which would benefit the whole scientific community. But this is at odds with individual interests, which include generating the most impressive and publishable results possible and minimizing project timelines to save on cost and effort. So this professor concludes that this misalignment of incentives hampers the adoption of best practices and robust methodologies, creating barriers to consistent reproducibility and ethical AI in biomedical fields. So we've been talking about research errors that lead to paper retractions, but another concern is whether we even know that a paper has been retracted when we try to use it, especially when we use LLMs to retrieve those papers for us. So a group decided to tackle this in a study from last year. So they identified 93 retracted articles, and they selected 3 large language models. And one at a time, they asked each model, they prompted it to find each retracted article. They did that by using prompts structured as which study concluded XYZ, and XYZ was taken directly from the conclusions of the retracted article. Now, the first question is whether the LLM found the retracted article, and that's not the rates I'm showing you here. These are rates for the second question, which is when the LLM did find the retracted article, how often did it notify the user that the article was retracted? So ChatGPT notified the user that it retrieved a retracted article 64% of the time, only 46% for Grok, and DeepSeek says 0% here, but that's hiding a bit of information. So the issue there was that out of these 93 test articles, DeepSeek only found the retracted article that it was supposed to one time out of the 93. And that single time it did not notify the user that the article was retracted. And then another major concern when using LLMs in literature searching is, of course, fabricated results. And this study looked at that as well, which is what is shown in this figure here. So this is showing out of those 93 test retracted articles, at least one of the LLMs mentioned a fabricated citation for at least 83 of those test cases. ChatGPT by far did the best here with only fabricating citations in 5% of cases, Grok in 16%, and DeepSeek 88%. So these results drive home something that I think a lot of us already have a sense for, which is that current LLM results cannot be accepted without a healthy dose of scrutiny, going back to our trust and scrutiny scale. when it comes to finding research out citations. All right, and with that, we'll end just briefly with a note on some of the human costs of AI in contexts like this. And these come from an interesting article that was published by a scholar at the Wharton School at UPenn, who focuses on leveraging AI for social good. And she describes what she calls the AI efficiency trap. And this is a process that proceeds in stages. So stage one is called initial productivity gains and experimentation. And this is where the organization and the workers have a lot of enthusiasm for the time savings that they are newly able to achieve with their AI tools. They have full agency over exactly when and how they are deploying these AI tools. And then comes stage two, managerial recalibration and integration. So the use of these tools then becomes normalized to the point where workload expectations scale up commensurately. So now workers are no longer saving time. Any time that they saved has become the new normal. Next comes stage three, dependency acceleration and systematic reliance, where similar to what we mentioned in a previous example, when these workers are not practicing the skills that they have trained for, the idea is those skills may start to atrophy over time, leading us finally to stage four, performance expectation lock-in and AI addiction, where the workers cannot effectively function anymore without their AI assistance. They've lost the ability to do that, leading to anxiety and ineffective productivity if and when those AI tools were to become unavailable. And this all ties back to this concept of agency decay, or the erosion of a person's ability to make decisions and function without their AI tools. So the takeaway here is that when groups pursue AI integration with the singular goal of maximizing performance efficiency, this can have negative consequences on the people involved. And this is because the level of AI utilization that may correspond to peak organizational performance does not necessarily equal the level of AI utilization that is going to be optimal for the workers' well-being. So teams and organizations have to be mindful of trying to balance the well-being, integrity, and long-term performance of their workers with the productivity gains that they can achieve with AI. And thus we come back to Spider-Man. With great power comes great responsibility. The successful use of AI will require both technological solutions as well as human considerations. So some of those technological solutions can include creating AI tools that are more transparent about the limits of their knowledge and the uncertainty of their responses, and tools that more actively solicit information and participation from the user to reduce the uncertainty of their responses. So with things like LLMs, you can imagine, rather than a simple answer machine, something that acts more like an honest assistant that actively works with the user towards a solution. And on the human consideration side, people who work with AI tools need to have better AI literacy. They need training in how to use these tools, or in understanding the limits of the tools and the risks that can result from their misuse and over-reliance. And they should be encouraged to work with AI tools in ways that actually complement their skills and expertise rather than replacing their skills or filling in for skills or expertise that they don't actually have. So thank you very much for your attention, and we can open up to questions. I don't claim to be any kind of expert on this topic, so I don't know about answering everyone's burning questions, but we have other people in the room here, so we can at least open up comments for discussion.
Do you maybe have personal perspective or opinion on less thought or lower risk applications in your own work that maybe you would be willing to recommend?
Yeah, so if people listening online couldn't hear the question, it was whether I have recommendations from my own work of less risky ways to integrate some AI tools into how I integrate them into my workflow and things I might recommend. So I would start by saying I fall quite high on the scrutiny side of the scrutiny to trust scale for AI and automation. So I've been a rather slow dinosaur-like uptaker of these tools. But at this point, I do use them a lot for coding assistance. So um, I try to think about LLMs as a shortcut for searching the internet for answers. So when I code now, a lot of times I don't have to look up syntax anymore. I can just ask my LLM to provide an example of what I'm trying to do so I can see with high reliability what the proper syntax is going to be, and then I adapt that to my own use case. So I'm a big fan of using AI tools to shortcut the generation of coding that I need to do, but I have a pretty strict rule against ever implementing code in any sort of moderate to high stakes scenario without having gone through it line by line and making sure I know exactly what it does. So I never take the results and apply them blindly. So I think that's one important piece. And then another one I already really talked about a lot with the literature search. Um, I only sometimes use LLMs to try to shortcut my literature search process. And I know there are some other tools out there. What's the rabbit one called?
Research Rabbit.
Research Rabbit. There are tools like that that are more specifically designed for this and I think can be more effective. And I do want to start exploring those a little bit more. But with just looking up some basic information or asking an LLM, can you find me any peer-reviewed publications that talk about this? Usually, even if I say that, what it gives me back are popular media articles, not peer-reviewed scientific publications. Um, but so I only try to use AI tools with literature searching sparingly at the moment, and I usually find the results not that helpful. Um, so in those cases, I would say, sure, it's fine to go ahead and try them, but you need to thoroughly vet any results you're considering actually using.
Um, there's a question on related to using various AI and AI adjacent tools related to literature searching and the tendency of tools to hallucinate specific papers or DOIs. Um, is there any efforts or attempts to ameliorate that in these types of tools and improve, say, like the return of actual papers and reduce hallucination and just papers that you're aware of?
Yeah, so we're addressing a comment from the chat about efforts to reduce hallucinations in AI tools extraction of literature search results. And I don't know about this in detail. I do know I read a little bit about some ideas to change the way that LLMs can be trained, or rather how they're fine-tuned, because the way the LLMs tend to work right now, they go through this huge pre-training process where they just learn a lot of general knowledge from the internet and how to use human language. And then they go through various stages of fine-tuning after that. And part of that is where they uh, they produce all of these responses that are then reviewed by human reviewers, and the reviewers tell them, this is a preferred response, this is a not preferred response. And that's how these LLMs learn to try to be so helpful, to try to avoid disagreeing with the user. So they try to always appear to be a super helpful assistant that's always finding something and trying to agree with the user whenever possible. And that's part of what leads to all of the hallucinations that we see, is that the LLM is so incentivized against disagreeing with or not providing something that the user asked for. So there are ideas about adjusting that fine-tuning process. As a four-letter acronym. Let's see. Reinforcement learning from human feedback, something like that, I think. and to adjust that so that we're not just fine tuning our models to be so prone to agree with us, but rather fine tuning them to be more transparent about what they don't know. So instead of giving us something made up, they might just say, no, I can't find that, or I don't know what that is, or would ask us for follow up to keep trying. But yeah, that's about the only thing I know specifically on that topic. If anyone in the room here has more knowledge on this, they can chime in too.
I think it's worth noting that
You'd come up here if you're going to say it, though.
I think it's worth noting that there's somewhat different performance now by different tools. So for instance, more generalized tools like ChatGPT, which are not specifically trained for application on biomedical literature, at least is where I noticed the most hallucination. But more recently, Google Scholar, for instance, has its own LLM that you can use for literature review, which is, from my experience, much closer to a discrete RAG application where the results are limited to its actual body of data. Or the temperature is turned down to the degree that it's only returning results from its training data set. And so I think your results on hallucination can start to depend somewhat on the tool that you're using and how that tool is tuned.
Couple questions about the human well-being element. One, um, just saying like it's not. They want to make sure that it's not just about, or it's really more about how work is done in the workplace, and more so how somebody feels about AI personally.
Mm-hmm.
And then the other question is how human well-being in the workplace relates to increased risks of a negative impact on data quality due to a reduction in human oversight.
Oh, I see. I think I see. So yeah, so one issue there sounds like they're highlighting is that uh, when there's heavy expectations put on workers to start using a lot of AI tools, sometimes they can be rushed into using these before they have the proper training to use them appropriately and effectively. And if they're under a lot of pressure to produce quickly using tools that they're not comfortable with, or tools that are not even designed well enough yet, that could add to issues where they're producing poor results. They're adding more noise and error into the systems rather than yielding good results. So I read a couple papers recently about this issue in the field of data science, where data scientists, many of them have just accepted that their field is moving towards heavy automation to the point where this makes them much more acquiescent to integrating AI tools quickly into their work because they feel like it's going to happen eventually. I might as well just say yes, even if I'm not comfortable with all these tools. And yeah, that can lead to problems.
So there's more of a methodological question that I think would be good to talk about. So this person basically spent some time talking about the tendency or really the need and the expectation, the standard practice in inferential statistics to do some amount of justification of your model and your model specification with an eye towards things like causality, temporality, and confounding. And then they say, is this not standard practice within the use of AI and ML?
Yeah, let me see if I can quickly summarize that question. So it was referring to how in more traditional inferential statistics, when we publish papers that use those methods, there's often an expectation to justify the statistical decisions that were made and the tools that were used. And are there similar expectations for this when we're using AI and ML methods? And I would say not as much is my experience of it. And now, to be fair, I've also seen many cases where in publications, the traditional statistical methods that were used are really provided with little to no justification as well. But I haven't seen a lot of this in the ML work that I've reviewed or read. So part of this has been an issue, I think, where there's just a paucity of reviewers who were actually had appropriate expertise in machine learning methods. Some of them might have just enough expertise that they're somewhat comfortable reviewing what you actually did, but they're not so comfortable that they can ask about or review what you did as opposed to what you could have done. So I think that could be part of the issue of why we're not seeing more pushback from reviewers for the authors to justify the AI and ML related decisions that they made in their research processes. Yeah. And Peter has additional comment.
Yeah, I mean, I don't know that the person asking the question is stating it in these terms, but I do feel like at times there is a tendency or a simplification of inferential statistics, good and well specified, and machine learning, bad and not well specified. I think it's worth noting that there's lots of bad inferential statistics that get thrown out and applied. And to JP's point, they're not always specified or justified. So even think about things like, automated model specifications. So things like stepwise regressions and things like that. Like there's lots of automation and other types of things that happen in inferential statistics that are sometimes justified and sometimes not. And I think, again, what you just see is, from my eye, I think something similar between any of these technical areas that wind up getting used or applied in biomedical fields is that there just aren't a ton of people that are capable of doing both the deep clinical justification as well as the technical application. And so even in, inferential statistics, I think you see people that are really deep at times in the technical area that don't necessarily do a good job of specifying their technical applications, or you see a lot of work that's relying on correlation as opposed to causation. So even in things like epi, where there's an expectation that you're doing more causal-based work, I mean, typically you see people working really closely between clinical experts, usually clinicians, working with the methods experts that are epidemiologists or biostatisticians or other sort of technologists. I think the exact same thing applies to ML and AI. You see good applications of it where, there's a small number of people that are capable of sort of doing it themselves across all of these multiple areas, or larger teams that are sort of working together to work across these sort of deep areas. So yes, I mean, I do think that there is an expectation in any technical area that you are justifying your work. But I think it's difficult to do that in increasingly technical areas. And I also think if we're seeing more of it in AI and ML, it might just be that those are particularly new and sort of attractive, high application areas right now where lots of people are flooding into and lots of work is happening, and not necessarily all of that work is happening, I think to JP's point, well, or at a rigorous sort of application so far.
I think we've talked about this in previous seminars too, right? Where you have people that are training in clinical fields or health-related research fields, and they're asking this question, do I need to become an expert in machine learning and AI? And, that's a lot on top of whatever field domain expertise they're trying to acquire. And so I think a lot of takeaway that we've been hearing is that anyone who's touching AI and ML methods probably needs some baseline level of literacy, but the solution ultimately is probably not going to be that everyone can have as deep of expertise as is required to really utilize these methods appropriately. and rather it's more that you have to bring together teams where you have people that have developed the deep expertise in the AI methods along with the people who have the domain expertise. Would you say that's accurate?
Yeah, I do think that's accurate. I mean, I think for those of us in the data science lab, there are areas that we work in a lot. So like historically, we spent a lot of time working with N3C and Recover on COVID and COVID data. I still don't think any of us would want to sort of run one of those projects without someone with more clinical expertise of COVID and sort of pulmonology clinical areas. And I think the same thing would be said, a clinician that has deep expertise. I think for a lot of them, it would be tough to run one of these data science projects on their own without somebody a little bit more knowledgeable on the data science application side.
Another question. May provide some of this type of training guidance for our UNC research community. And there's another question, just saying same thing, kind of like some very useful. We'd like to see more training on it.
Yeah, so in short, I would say you're looking at it as part of the answer. So I did put the link up here to where we post recordings from these seminars. There's a bit of delay on them. So like this seminar, for example, might not be posted for about a week or so. But this is where we will be accumulating such seminars over time. We also have a SharePoint site associated with the TRACS Data Science Lab, where we try to post some educational resources on a variety of data science related topics, including AI and machine learning topics. So we're trying to post some resources to the SharePoint. We're trying to do some of these seminars and panels to provide some of that education. And we want to continue to do more of that. And we're happy to take suggestions from anyone who has ideas on educational content or training that the TRACS Data Science Lab might be able to assist in providing. So we do have a website as well. I don't have the link to it here offhand. We can drop it, in the chat. And we've got a couple links scattered around the website there that have options for you to send feedback to us if you have suggestions for seminar topics or other educational content. So yeah, happy to take those recommendations through that way. Or I've got my email on the screen here. You can also email them to me. With that, we're pretty much at our time. So I say we'll go ahead and wrap up for this month. Do you want to say anything about next month?
No, to be done.
Yeah.
Fourth down.
All right. Thank you so much for attending, everyone.